All right, this is Basic Concepts in Chemical Bonding, Part 2 by Mindy Bedrosian. Please remember I'm only going over a few of the high points. You still need to read the chapter to really get all the material. This is just like a little quickie pieces and parts. A little reminder, covalent bonds. This is when electrons are shared. It doesn't mean that they're shared equally, however. It just means they're not quite ionic. So the electrons are not always shared equally. Sometimes one partner is more electronegative than the other. That means they pull the electrons towards them. Let's take a look at a water molecule, H2O. You could see that hydrogen has, each of them is sharing an electron. But oxygen is more electronegative, meaning it really likes to pull the electrons close. It's still sharing, but not evenly. And you can see that in the next picture, there's the electrons closer to oxygen than to hydrogen. Those little squiggly marks there mean slightly, slightly negative, slightly positive. So since oxygen has electrons pulled closer to it, it becomes slightly negative on that side. And the hydrogen's electrons are a bit further away, so they're considered to be slightly positive over there. So now one side of the molecule is just a teensy bit positive and the other side's a teensy bit negative. And you probably recall this is known as being polar. And it's like dissolves like. Polar molecules dissolve other polar molecules. And nonpolar dissolves nonpolar. Oh, I found a cartoon. Haha. All right, let's move on to looking at Lewis structures, since this stuff here is all related. And with Lewis structures, everybody wants to be a noble gas. They're the coolest ones in the high school. Everybody wants to be a noble gas. Why, you may ask? Because they're super cool. And because their outer or valence shells are full with electrons. Some things to remember when you're drawing Lewis dot diagrams or Lewis structures. Pair electrons to form a bond. Satisfy the duet rule for hydrogen and the octet rule for second row elements. Boron and beryllium are, they often have fewer than 8 electrons. And they're highly, highly reactive. So in chemistry, there's always a couple of exceptions to the rules. Here's exceptions to the octet rule. BF3, SF6. So sulfur uses its empty 3d orbitals to stuff electrons in. And that's how it does it. So it accepts more than 8. So we're going to take a look at a couple of examples. The third row can exceed the octet rule because they use the empty d orbitals to put electrons in. So here's one, PCl5, 2, 4, 6, 8, 10. Phosphorus has 10 electrons, not 8. And so it's a third row element. It's accepting more in its d orbitals. Chlorine, 2, 4, 6, 8, 10. ClF3. It's also accepting extra electrons. What about this one? This is BeCl2. This one is deficient. This is beryllium. It's a special case. It's deficient. It only has 4 electrons in its shell. This is XeO3. What do you think? This is obeying the octet rule. 2, 4, 6, 8 electrons. And RnCl2. What do you think of this one? This one is accepting extra electrons in its outermost shell.